So let me announce. So today we have a presentation by Duvan Cardona from a PhD student at Ghent University in the analysis and PDE group about mathematical analysis, medical image processing. So Duvan, please start.
Thank you, Professor Chansky. Then I'm going to present. A very introductory talk about mathematical analysis in medical image processing. We have two goals with this talk. The first one is describe the different image modalities used in medical diagnostic when specialists use medical imaging in order to give correct correct clinical analysis and in order to do suitable medical interventions. The second one objective is this objective maybe is more close to us is how mathematical analysis appear in this context. In particular, we will discuss how some approaches using tools of PDE can be used in this context. To do maybe more attractive this talk for us, let me present some interactive videos, maybe short videos, where we can obtain from specialists very precise information about how the different kinds of imaging modalities works. And after that, I will discuss how PDEs, some linear and nonlinear PDEs appear in this context. For example, in order to remove the noise of some medical image. Imaging modalities are based in different physical principles. These techniques can be more or less useful when studying a particular organ or pathology. And in practice, they are very complementary because they offer different features into the same underlying reality. Imaging modality that specialists use is ultrasonography, computer tomography, magnetic resonance imaging, positron emission tomography. Ultrasonography use high frequency sound, ultrasound, maybe waves between 20 megahertz and 2000 megahertz to produce an image of internal organs. It is useful to study, for example, anatomical change in pregnancy, for example, because ultrasound can distinguish maybe subtle variations aim on soft fruit-filed tissues. It is particularly useful in imaging the abdomen. In contrast with X-rays, for example, ultrasound does not produce maybe the image on tissues with ionizing radiation. Yes, it's a good advantage. But a great disadvantage of ultrasonography is that it produces very noisy image. This is one example of the medical device that specialists use for taking this kind of modality of imaging modality. This is one example of stationary ultrasonography, and this is maybe the superposition of several images of this kind. of this kind. Let me show you this video about ultrasonography from one specialist. Everyone can hear? Ah, sorry.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Okay. The other modality for imaging, medical image is computer tomography. Computer tomography is a number of two-dimensional radiographs which are acquired by rotating the X-ray tube around the body of the patient, like we can see in this in this image with this medical dispositive. This is one CT computer tomography scan. A computer tomography is essentially a 3D version of X-ray radiography, and therefore offers high contrast between bones and soft tissues, and low contrast between different soft tissues. Let me share this video of some specialists explaining us maybe how the scanner of CT of computer tomography works. Maybe.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
The mathematical tool arising in computer tomography. I will not speak about this mathematical tool in this talk, but it is the radon transform. I will speak about the radon transform maybe in a future opportunity. Now, let me go to magnetic resonance imaging. This technique relies on the realization properties of magnetically excited hydrogen nuclei of water molecules in the body. The image created with this modality can be created by using the realization rates in different tissues. MRI use strong magnetic fields and non-ionizing radiation. Yes, different in contrast with computed tomography, for example. This is one example of magnetic resonance imaging. Yes, that we can see. Let me finish these two medical imaging modalities, presenting two more videos about how these two modalities works.
MRIs use protons, which are abundant in the human body. All protons spin, creating a small magnetic charge. When a strong magnetic field is introduced, as is the case in an MRI machine, the protons align with that field. The MRI technician then introduces a radio frequency pulse that disrupts the proton and forces it either into a 90-degree or 180-degree realignment with the static magnetic field. Since the radio frequency pulse pushed the proton against its nature, once this pulse is turned off, the protons realign with that magnetic field, releasing electromagnetic energy along the way. The MRI is able to detect this energy and is able to differentiate various tissues based on how quickly they release energy after the pulse is turned off.
The last modality in medical image is positron emission tomography. This technique consists in injecting to the patient some radioactive isotopes emitting particles called positrons. From the position and delay between a few photon pair on some receptor, the origin of the photon can be determined. Let me finish this part with the following video about how this positron emission tomography works.
Scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
this is one example of one tomography of this kind. Okay. Now, in that follows, I will present maybe the more mathematical part of this presentation. So let me describe how we can study one image from the mathematical point of view. One image is one function, yes, where this function is a function from some domain of R2. This maybe is one rectangle, yes, maybe the unit rectangle on R2, or some subdomain of R2. C, which is the range of the map, is the space of colors. Then in gray, here we have only pictures in gray scale. Then we can think that the space of colors only is a subset of the interval 0, 1, where 0, we can think of 0 like the white color, and 1 the black color, and the other values between 0 and 1 are the different colors that we have in one grade scale. And how we can see in this cube, here we have, for example, that this map, this image is one function from D to C, and C is a subset of R3. Yes, a subset is more specific of the unique cube on R3. Then this is a good maybe modulation, good definition for color image having color, where we have in the inner of the cube all possible colors. Then the question is, here we have this definition of image. Why we can use PDE for the processing of image, in particular of medical image? And the answer is that we can use PDEs because here we introduce one artificial time. Then one pictures, one image can be deformed in time. Then this deformation generates a discrete or continuous sequence of image, yes? And maybe one can think about which suitable PDE can be using for modeling this the evolution of this sequence of image, yes, where the initial condition is the initial image that we have. Then we can think that we can propose one model of this kind, where I is IHT describe the evolution of this image in some time t, where t belongs to some interval, and this operator f in this partial differential equation is characterized, can be characterized by the given algorithm. One motivation for this kind of models, PDE models, is Gaussian filtering. Let me explain what is this? Here we have one image, inode, here. Then maybe we have some noise on the image, and we can remove this noise by using some regularization process in the image. For this, for example, we can use the convolution operation between functions, because we are working with functions in this context. This Gaussian, if we remember, this Gaussian is exactly the appear in the fundamental solution of the heat equation. Then this family of convolution with the initial image that we denote here E sub Tx satisfy the heat equation, but from the technical point of view, when one applies regularization, some noise in the interior of the picture can be removed. Some maybe not important information, some noise, but the problem with, for example, the problem with Gaussian filtering is that Gaussian filtering don't have good properties near to the boundary, near to edge, or near to boundaries around of the image. For example, if this is one initial condition or image, and we regularize with this at this time, we have this filtering, and if we regularize maybe with this better time, then we have a better result here. Then PDE appear as a natural way, maybe a natural technique to smooth image. But as I mentioned before, if this PDE is linear, maybe is given by some convolution, with some family of functions, then maybe this processing is not good. It's not good for edge and boundaries of the image. Then one needs maybe to solve this problem, making the convolution nonlinear, or modifying the heat equation, or maybe redefine the problem of evolution of the image, like defining one optimization problem. Yes, defining one optimization problem. Then for the first solution, if one wants to make maybe the solution to be nonlinear, we can use models like the models of Tomasi and Manducci, where they take over. Let me denote the initial image, like in U naught. This is E sub naught, E naught, and then one operates, one apply this kind of process in the initial image, putting some weight here, and this weight is defined in terms of two functions, d and tilde d, characterized specifically by the algorithm that one is using. This is one solution. With this kind of solution, one can improve maybe the noise of some image in boundaries. We can maybe remove non important information. The second one solution that I mentioned before was to modify the heat equation. based in Gaussian filtering, yes? Because we know that Gaussian filtering is maybe efficient in the interior of the picture, in maybe regions far from boundaries and edge. Then it's a good idea to modify the heat equation. We can write then the Laplacian of U in this form, but if we put some additional term here, maybe we can obtain better results. That is the objective of this talk. Maybe is to describe how we can modify this kind of equations in order to study the processing of medical image. To modify the heat equation, Peron and Melik, for example, they introduced this model where one put here one nonlinear term, and C is one constant. This constant, okay, maybe this depends on time. This depends on time, and this is the kind of regularization that one can obtain with this model, which looks very efficient in regions of the picture near to the boundary and near to the edge. And the third solution for this kind of problem is to redefine the problem, the initial problem, like one optimization problem. Yes, we know that, for example, the heat equation can be characterized by using variational inequalities, by minimizing one specific functional. In the case of the heat equation, one wants to minimize the double integral of the norm of the Laplacian of U squared. And when one minimizes this functional, then one obtains the solution of the heat equation. Yes. Then, using a similar idea, then one try to minimize some suitable functional. And the important part with this in this solution, in proposing this model, is to identify the kind of differential equation that one can use in the minimization of this problem. Then, for example, one can use equations of Euler-Lagrange type, yes, where, for example, the minimization problem is associated to this kind of linear equations. Then maybe I will finish for today this presentation. Next time maybe I will give more details about how this kind of models operates, and also how the radon transform appear in computer tomography. Then thank you very much.
Okay, thank you, Duvan. So basically, just to summarize, so you had so there is, of course, there are variational models, and there are also PD models, and then they can be related by Euler-Lagrange equations, but they don't have to, right?
Yes.
So there are many methods and techniques, and yes, we hope to continue this topic maybe next time with more details, but thank you.
Okay, thank you.